Hi, everyone. Let's review rationalizing denominators and also numerators. So when we rationalize the denominator of a fraction, we eliminate radicals and non-integer exponents. Like, for example, the square root of 2 is 2 to the 1/2, right? In the denominator, but possibly introduce them in the numerator. So you may end up with radicals on the top. So for example, in trig, you may know 1 over the square root of 2 as the sine or the cosine of 45 degrees, but this is unacceptable in a simplified expression to have radicals in the denominator if you can rationalize the denominator. So if you have the square root of a non-zero positive integer there, then you should be able to rationalize the denominator. So you take the 1 over root 2, you multiply by 1 creatively, root 2 over root 2, and then you multiply, this is 1, you're multiplying by 1, right? And then you multiply across. 1 times root 2 is root 2 up on top. On the bottom, root 2 times root 2 is root 4, or just 2. Basically, you remove the radical. So 1 over root 2 is equivalent to root 2 over 2. And this is more acceptable as a final answer, like in trig. Now, if you have something like 1 over the square root of pi, or 1 over the square root of x, then we tend not to pull a similar stunt because a pi itself is an irrational number, so there's no point in pulling a similar stunt for this guy. Likewise here, x itself could represent a messed up value, like pi. So we tend not to rationalize or try to rationalize the denominator if we have like 1 over root pi or 1 over root x. But for 1 over root 2 or 1 over root 3, we would tend to rationalize the denominator. Now, sometimes we want to rationalize a numerator, where we start off with radicals in the top, and then we want to end up with a fraction where we no longer have radicals in the top, but we might end up with radicals in the bottom. Okay, so for example, later on, when we find the derivative of the square root function, we have to work out this expression, and it turns out that we're going to want to rationalize the numerator. The problem is that if you let h approach 0, then both the top and the bottom are going to approach 0. That's a problem in calculus. So anyway, how do you get an equivalent expression where you rationalize the numerator? All right. Well, how can we get rid of the radicals up there? Students are often tempted to do this, squaring, but you're not allowed to do that. Because if you just have a single expression, you're not allowed to just square it. For example, if I take 3, can I just square it and say that 3 is equal to 9? Well, no, I can't do that. You might be confusing that with solving an equation. There's a difference between re-expressing or simplifying an expression and solving an equation. You're not allowed to square this whole thing just because you feel like it. All right, so what can we do? We can multiply by what magic number? 1, the multiplicative identity. When you multiply by 1, you end up with the original. All right. So here, we're multiplying by 1 creatively in such a way that we're going to remove the radicals on the top. Oh my gosh. So what's going on here? We're using the following multiplication rule. Remember that if we multiply a minus b and a plus b, we end up with a squared minus b squared. If you don't believe me, FOIL this out. Or you might recognize the factoring rule that goes in reverse. This is the factorization of a difference of 2 nice squares, a squared minus b squared. So we want to multiply the quantity root x plus h minus root x by its conjugate. You obtain the conjugate by flipping the sign in the middle. We're taking the copy, and we're flipping the sign in the middle. Root x plus h plus root x. And to be fair, we're multiplying on the bottom. That's how we multiply by 1 overall. Now, the idea is that when we multiply these two tops together, we're exploiting this rule, something minus some other guy times something plus the other guy. The product is going to be a squared minus b squared. And what are the squares going to do with these radicals. They're going to end up removing them. There are domain issues, like we need the radicands to be non-negative, but let's not even go there right now. So when we multiply a minus b, I'll write these in. When we multiply a minus b and a plus b, we end up with a squared minus b squared. On top, a squared minus b squared. The square of the first guy minus the square of the second guy. The square of the square root of x plus h, which is what? It's just x plus h. Let's put grouping symbols to be safe, although we don't need them in the end. Minus the square of root x, which is x itself. If x is non-negative, but let's not worry about that. Your denominator is ugly. Remember, you have h times all this junk in the bottom. Your denominator is ugly. Even I forget that sometimes. That's wishful thinking to forget this piece down here. So in the top, we have the quantity x plus h. It turns out we can remove the parentheses. They don't help any. Minus the x over here. Over that product. Well, what's x plus h minus x? These cancel. They add up to 0. We end up with h on the top. And when we end up with h on the top, now what can we do? We can cancel or divide out. H is a factor of the top. It is the top. H is a factor of the bottom. We can now do this. H divided by h is 1. Top and bottom. By the way, h does not equal 0 is a hidden restriction, but we're not even bothering with domain on this problem. We end up with, don't engage in wishful thinking. We do still have a 1 on top here. We do still have a fraction. We have a 1 that survives on the top. A lot of people forget that. 1 over this piece here, root x plus h plus root x, where h is not 0, the hidden restriction. And yes, these two radicands must also be non-negative, but we won't go there. So notice that with the original over here, we had radicals in the top, but not the bottom. We end up with, here, radicals in the bottom, but not the top. But see, in calculus, and in this class, we're going to let h approach 0, and we're going to end up with 1 over 2 root x. Why do we care? That's the derivative of the square root function, given by f of x equals root x. That's in chapter 1. Don't worry about that now. Bottom line, when we rationalize the numerator, we end up with this. The derivative stuff we'll talk about later on. We do prefer this in calculus. In section 0.9, I end with common errors. Common mistakes like root a squared, don't forget the absolute value, things like that. But these are common things, common errors to watch out for, forgetting absolute value, for example. Also, the idea that the square root of a sum equals the sum of square roots. No, you do not take square roots term by term. Likewise, exponents cannot be shared for a sum or a difference. Be careful when factoring. You share the factor or the radical, basically. Be careful with canceling, right? We cancel equivalent factors of the entire numerator and the entire denominator. We do not take reciprocals term by term. Okay, so the reciprocal of the reciprocal of a plus b, that is 1 over a plus b, that's not 1 over a plus 1 over b. That doesn't work. It doesn't split up like that. Over here, remember, a fraction bar implicitly groups its top. So if you have something like this, when you subtract the fractions, don't forget the grouping symbols over here. Because when you subtract the numerators, you're subtracting the group b plus z. Over here, remember that the negative exponent does not apply to the 7. X to the negative 4/3 pops up as x to the 4/3, but the 7 down here, that stays down there as a 1/7. It does not pop up as a 7. The negative exponent does not apply to the 7. We discussed that before in section 0.5. All right, next up, some more gymnastics in section 0.10.